Good morning. I will start today with chapter 26. And for chapter 26, we're going to see that mostly we are going to talk about optical instrumentation. And, one of the most important optical instrumentation is our eye, okay, the human eye. And then we are going maybe to talk about like what is really the major structures in the eye. Like the first video is going to be only physics of the eye. We're going to explain also how the image is forming, and we are going to talk about really the refractive indices related to different parts of the eye, and analyze the accommodations of the eye when we have distant or near vision. Okay. Now, the second part is going to be about vision corrections. Everybody, I think, in the class know about the farsightedness and the nearsighted, and we're going to see how we are going to correct these, and what will be done. The next topic is going to be color and color vision, how we can, say something about color vision, how really the theory explaining how we see colors, and then outline the coloring properties of light sources, and describe also the Retinex theory of color vision, and how really we like view colors. Um, in microscopes and telescopes, we are going to talk about how really we can form an image from an image. Okay, then we're gonna have like double, or we call it composite images, and finally aberrations, which are really the kind of limitations to optical instrumentation, and talk about how they're gonna affect the instruments that we use. Now, the first thing is here. I'm gonna maybe mention mostly I will say the most important parts: the cornea here, the lens, the aqueous humor here, and the vitreous humor, fovea, and the optic nerve, and the retina. Okay, these are the most important part for us at this stage. And here, just we're gonna say that the light is coming into the eye, and the cornea and the lens, they are going to form kind of a thin lens system that is gonna form a real image on the retina. Now, retina is very rich with cells that they are really receptors of light in the fovea, and they are gonna send this information to the optic nerve, and the optic nerve is gonna send it to the brain, and the brain is gonna recognize the image. Now, this is very important, like the power of the lens, it is adjustable. Okay, then it will adjust to provide an image on the retina for different distances. You don't have like to be at a certain distance in order to see things. Okay, our eyes are making these kind of accommodations. Okay, we will talk about these here from physics of the eye. It is considered an optical instrument. It can actually detect so many details, and also it can detect colors as well. Okay, now the first part, as I said, the cornea and the lens, they form a single thin lens system, and that is really adjusting the power to produce an image on the retina. Now, the center of the image falls on the fovea, which is a greatest density of light receptors, and is going to be, forming a sharp image of the object that we are seeing. Now the pupil is going to be like a control that is, it's a variable opening that is really going to make the eye detect the light intensity and adjust. Okay, then it can adjust the intensity of light from lowest observable to a 10 to the 10 times greater, which is a very wide range. The eye can do all the following. It can sense direction, it can sense motion or movement, sophisticated colors, distance as well. Okay, then we sense by our eyes, we sense all these. Now, the process of visual nerve impulses begins with when we're going to have these interconnections in the retina, and it will continue in the brain, and then it will convey the signal received by the eye to the brain, and the brain is going to make on actually I will say flipping the image again, because the image is going to form the initial image on the retina is going to be upside down, inverted, and then we're going to have this inverted again. Now, these are the different media that we're going to have in our eyes, and the materials. Look at the water, of course, we know that 1.33 index of refraction, the air is 1, the cornea is 1.38. And something that we need to notice that like the light is coming from air and then it's going to hit the retina, then it's going to here face a very sharp or a very large change in index of refraction. Therefore, it's going to bend. The bending is going to be more. Okay, of course, the aqueous humor, it has this 1.34. The lens, it has an average of 1.41 because it's going to be, that the thickness of the lens is not actually, just a constant. It is changing. The vitreous humor is going to be 1.34. Now, we're going to say, and we did learn this when we were talking about lenses, that image formation using lenses depends on refractive indices, because this is going to tell you how much is the light is going to deflect or bend. The biggest change in refractive index and bending of light occurs at the cornea rather than at the lens, because as I told you, like we are coming from air, which is 1, to the cornea 1.38, if I still remember. Yes. Okay. And the cornea provides about 2/3 of the power of the eye. Okay. Now the rest of the here, look here what we have. Like we have like a tree, and the lights is gonna come to the eye. They're gonna bend, and they're gonna have several bending. Here is gonna bend from air to cornea, and then from cornea to lens is gonna bend through the liquids. Also is gonna bend as well. And you're going to see that the image is going to form that it is inverted. The lens provides the remaining power of the image, and the right rays pass through cornea, aqueous humor, several layers in the lens, and vitreous humor. And every time it's going to change direction or bend. And it's like about each interface, and that as if we have a single convex lens. Okay, it's a very complicated system, but it is equivalent to a single convex lens, and the image is going to form on the retina. It is inverted, but the brain invert them once again to make them seen upright. And this is here, we look at how really the relaxed vision versus the accommodated vision is going to be making accommodation in the eye based on what? Based on the distance of the object. DO, it is the distance of the object. When the object is very far, This means that DO, the distance of the object, is very large, and then the light is going to come parallel and it will converge because of the lens. But look at the lens, and here when the object is very distant, is close, I mean, the of the object is very small, the lens is gonna be changing, you know, and therefore we're gonna have this type of image. It's gonna diverge and still enter the eye, and the both images. And we are talking here, of course, about a normal vision and a person without any let's say defaults, or you know, like, yeah, good vision. The image must fall on the retina to produce clear vision, and the eye, it is the lens to retina distance, and the eye must be the same for all the objects, because the eye, like the eye size, is really the same. Now we know that the eye manages this by having what is called accommodation, and that is really adjusting the eye's focal length, which is the lens, and this is done by like the changing the shape of the eye. Now, a person with a normal ideal vision can see objects clearly at distances ranging from 25 centimeters to infinity. Okay, then if you have you know, like somebody with a normal, you know, without any you know, like nearsighted, like, or farsighted thing, they're gonna see things from 25 centimeters to infinity. We define here the near point, which is the shortest distance at which a sharp focus can be obtained. This distance is increasing with age, and therefore we're gonna, you know, put things away from our eyes, like more distance, because that near point is gonna change. Now, this is the equation of lenses that we did use before. 1 over f equals 1 over the distance of the object plus 1 over the distance of the image. This is the magnification equation, all right? And of course, it's the same idea for problem solving. What is the size of the image on the retina of a 1.2 10 to the negative 2 centimeter diameter human hair, held at arm's length 60 centimeters away? Take the lens to retina distance to be 2 centimeters. This is a standard. Okay, then y, this is the height, 1.2 10 to the negative 2. Here you know, because I'm used to use u for distance of the object and v for the distance of the image. Okay, then u is 60 centimeters and v is 20 centimeters. U, it is the DO, which is the object distance, and v, it is the DI, or the image's distance. And this is the magnification. We know that when the magnification is less than 1, it is reduced. When it is 1, it's the same size. And when it is greater than 1, it is enlarged. Now I can calculate the image size, y prime, from, you know, having this equation here, minus v over u times y, and that is negative 2, okay, because this is the image's distance divided by the object's distance, and there is a minus built in the equation, times 1.2 10 to the negative 2, and that is really negative 4 10 to the negative 4 centimeters. And this is telling us that it is inverted, and actually it is, of course, reduced. All right, okay. For the combined system, when we have a combined system, we are going to have the total magnification is going to be M1 times M2. We did not start working with this. We're going to work on it in the next video. Here, the power range of the eye. We know that calculate the power of the eye when the viewing objects at the greatest and the smallest distances possible with normal vision, assuming a lens to retina that is 2 centimeters, which is a typical value. Now, in order to have a clear image, first, like for U, which is di, is going to be infinity. Power of the lens, it is 1 over f. And I put the equation here. P equals 1 over u plus 1 over v. And that is 1 over infinity, which is 0. And that 1 over 0.02. And then the power is going to be 50. This is for the distance vision. And for the close vision, okay, normal person, 25 centimeters. We're going to convert this into meters. And then we're going to find that for the close vision is going to be 54. That is for this video. Thank you and see you soon.